the quantum harmonic oscillator problem and its solution go far beyond the simple generalization of a particle in a spring problem in classical physics, and they appear in a variety of contexts in quantum physics, as already mentioned. For example, electromagnetic radiation can be thought of as a collection of harmonic oscillators, the photons, and much more generally, various complex structures in quantum mechanics oftentimes can be thought of as being built of the small building blocks, being a quantum harmonic oscillator. But in each particular case, the meaning of these individual oscillators is different. And today I'm going to show you the appearance of these quantum harmonic oscillators in the context of a very interesting problem that sort of underlies solid state physics or condensed matter physics. And this is a problem of excitations in crystals, which are collections of many ions that form a periodic structure. And these ions can oscillate, and these oscillations, quantum oscillations, are called phonons. And we will see how these phonons appear, and we will see also that they can be described in terms of the creation and annihilation operators that we introduced in the first lecture this week. To understand the concept of a collective mode, such as a phonon, for example, in a complex quantum system, we first can go back to classical physics and remind ourselves the notion of a normal mode, which is equivalent to the quantum collective mode. And these normal modes appear in complex classical systems. So here I have a primitive classical system. If you want, this is a simple harmonic oscillator. And in this case, as we know, the frequency of the oscillation is equal to the square root of the stiffness of this spring divided by the mass of this object. Now, if we make the system a little more complicated, and instead of just one oscillator, consider let's say two masses attached to let's say three springs in this case. So we have a system here with 2 degrees of freedom, and this system will have two different oscillation frequencies corresponding to different types of oscillator motion. So for instance, this type of motion, when the two masses sort of oscillate in phase with one another, so this let's say first type of motion is described by the frequency which is exactly equal to omega. But there's also a second type of motion that we can imagine in this slightly more complicated system, in which case, let's say, these guys oscillate out of phase in this fashion, sort of. And this oscillation frequency, let me call it omega 2 in this case, is equal to square root of times the basic frequency of these guys. So let's assume they all have the same stiffness. And we can make things more and more complicated, and let's say in this case have six masses attached to springs, and in which case we will have 6 different degrees of freedom and 6 different oscillation frequencies. So, and these oscillation frequencies, so-called normal modes in classical physics, they have an analog in quantum physics. In particular, let's say in this example of two harmonic oscillators, we just by knowing the results of the classical calculation, we can write down, as a matter of fact, the spectrum of the quantum problem, of the corresponding quantum problem. So, the spectrum of the corresponding quantum problem will be simply the energy is going to be equal to h omega 1. N1 plus 1/2, h plus h omega 2, and 2 plus 1/2, and it's going to depend on two quantum numbers, n1 and n2, corresponding to two harmonic oscillators. But these are not going to be directly the harmonic oscillators built out of, let's say, the coordinates and momenta of the two particles. So these oscillators, or the corresponding creation and annihilation operators, are going to be a certain non-trivial linear combination of these x1s, p1s, x2, and p2, which sort of describe the generalization of these in-phase and out-of-phase motions to quantum physics. And in general, whenever we have a classical system with some normal modes, there is a corresponding quantum system with the spectrum associated with these normal modes. A very interesting example of a complex many-particle quantum system is a crystal. We know that crystalline structures of various types appear in a variety of solid-state materials. And in these structures, so what happens is that ions or atoms of which this solid-state material is sort of built, they arrange themselves into a unique order and pattern. And so here, for instance, I'm showing a fragment of a so-called simple cubic lattice. And these blue balls in this picture correspond to atoms sitting on their equilibrium position on their lattice sides. But this picture is a bit deceptive. Actually, it's probably better to say incorrect, in that the atoms here in reality are not static. So they indeed have some preferential positions and some equilibrium positions, but they move around all the time. So this position that they occupy corresponds to a minimum in some effective potential they feel, but they can oscillate near the minimum of this potential. And these oscillations are basically described locally as essentially harmonic oscillator motion. So a better illustration of what a crystal is, so that I put together, well, for simplicity, for a two-dimensional case, so is presented here. So instead of thinking about atoms which are sort of tied together in this crystalline structure by some rigid objects, we should think about atoms being tied together by some elastic springs with some stiffness, which is finite. And so when we look at this system, so by analogy to what I had discussed, what I just discussed in the previous slide, we can think about this system as a many oscillator system with a lot of degrees of freedom. So in reality, in this material, so there are not 2 or 3 or 6 atoms like in the previous slide, but there are billions and billions of atoms. And therefore, there are many frequencies, eigenfrequencies, or normal modes, that classical normal modes that appear, and they correspond to various kinds of complicated oscillations in this system. And in the limit of an infinite number, basically so-called thermodynamic limit, when we consider essentially an infinite crystal, so these discrete normal modes, they merge into continuum curves, which essentially correspond to elastic waves running through this system. And mathematically, these waves are described by a familiar expression. So if we think, let's say, about the displacement of an atom with regards to its equilibrium position, some delta r as a function of time for a particular atom, let's say nth atom, so it's proportional to the familiar exponential of k dot r, so where this atom is located, minus omega t. But this omega is itself a function of k. And so to find this so-called dispersion, phonon dispersion, is the main question that appears in the context of this problem, and this is what is going to be of interest to us. Of particular interest is the question of what are the low energy modes of this system. So what it actually means is the following. Suppose we have a completely static crystal. So, well, as static as it gets in quantum mechanics, there is always zero-point motion, but we can even consider a classical system. Let's say we just physically built this model by attaching a bunch of masses to the springs and arranging them in an equilibrium pattern. And let's say we touch this system a little bit, we apply very weak perturbation. So the question I'm asking about the low energy modes is, are we going to excite any oscillation in this crystal, or this weak perturbation is not going to have any effect? Or in other words, do we have to overcome any threshold or gap, as condensed matter people call it, in order to excite the minimal perturbation in the crystal? And as we will see later in today's lecture, so the answer will be that it doesn't matter how weak the perturbation is, there is always a very low energy mode which corresponds to a long wavelength or small k wave running through the sample, through this crystal, This type of an excitation is called an acoustic mode, or it corresponds to sound modes running through this crystal. And it turns out that this appearance of these acoustic sound modes has a very profound explanation, which goes as far as relativistic quantum physics, actually, where there is a theorem called Goldstone theorem, which guarantees the appearance of certain low energy modes. And even though I'm talking now about classical system, let me nevertheless try to connect it to this theorem, but I will present sort of a poor man's version of this Goldstone theorem, which is relevant to our problem. And then hopefully we will be able to understand how they are connected. So this is going to be a little bit of detour. So the poor man's version of the Goldstone theorem that I'm presenting is related to the notion of symmetry in quantum physics that we already discussed. So suppose we have a quantum system which is invariant or symmetric with respect to a certain class of transformations. What it means is that there exist transformations, let me call them U, and this operator commutes with the Hamiltonian, which describes the system. So this is what it means. Or in other words, so U H U minus 1 is equal to H itself. And let me consider the situation when there is not just one or two symmetry operations that exist, but as a matter of fact, we have a whole family of such operations, let's say labeled by some parameter. Let me call it alpha. So an example of such asymmetry, for instance, could be symmetry with respect to translations. So let's say if our Hamiltonian is symmetric with respect to translating everything, every single particle in space, let's say by a certain distance, so it could be a distance of 1 meter or 1 centimeter, 1 kilometer. So there is a whole continuum of distances and directions in which we can translate our system, in which case this alpha actually is a three-dimensional vector of translations. Well, another example could be symmetry with respect to rotations, in which case alpha could represent an angle that we can choose by which we can rotate our system. But in principle, it can be anything. So we just basically postulate the existence of some symmetry, what is called symmetry group, but I'm not going to go into these details, with respect to which the Hamiltonian of the system is invariant. But a very interesting fact is that even though the model itself can be invariant under certain symmetry operations, the quantum states, for instance, lowest energy state or the ground state, does not necessarily have to be invariant under the same symmetry U. So what it means is that the system may find itself in a state, let me call it psi naught, such that, U acting on this psi naught is not equal to psi naught. So by translating, let's say, our system in space, we do not necessarily represent the same state. And in this case, we call we say that the symmetry is broken or spontaneously broken. But the key statement, which is also the statement of this Goldstone theorem in this context, is the following: if once again we have a situation where the Hamiltonian is invariant under a certain continuum of symmetries, but some or all of these symmetries are broken in the state in which the system finds itself, in this state, let's say psi naught, then to each broken continuum symmetry there corresponds a low energy mode, a sound-like mode if you want, that we just discussed. This statement, this correspondence is again the statement of this Goldstone theory. So I realize that there have been, a lot of words that I've said, but perhaps the best way to understand the actual meaning of these words would be to provide an example, which also will explain why this discussion is relevant to what we talked about before in the previous slides about phonons, crystals, and all these things. Now let us look at a crystal structure once again. So we have here a periodic arrangement of atoms, but nobody puts this crystal structure by hand, right? So if we have a piece of some solid material, let's say a piece of copper, so nobody builds it by hand, like atom by atom. We don't have to do it. So the nature does it itself. So these structures, they form spontaneously, and there is some wave function, if you want, psi naught, which describes well, very complicated wave functions, which describes this atom. So how do these atoms form in such a pattern? So this psi naught is a solution to a certain Hamiltonian that describes those atoms. And this Hamiltonian, it has, kinetic energy of all the particles involved in the problem, all these atoms, plus an energy describing its interactions. And very importantly here, the interaction, it depends only on the distance between the atoms. So here N and M, they labeled various atoms. Now, if you look at this Hamiltonian, so you see that if we translate the whole thing, if we, let's say, change R to R plus some constant distance, let me call it D, then the Hamiltonian is not going to change, since we have here only the distance between particles, which is the position of nth particle minus the position of mth particle. If we translate both of them by the same distance, the distance between them is not going to change, right? So therefore, in other words, what I'm saying here is that here the Hamiltonian is invariant under translations in real space by an arbitrary, it's very important, by an arbitrary distance. So, but if you look at the crystalline arrangement here, so it is no longer invariant under an arbitrary translation. So if I move my particles, let's say by a fraction of this lattice constant, I'm not going to reproduce the crystal. So the crystal is still symmetric, but it has a symmetry which is sort of lower. It has only discrete symmetry, while the original symmetry of the problem was a continuum symmetry. And that's a crucial difference. And therefore here we have broken, spontaneously broken, if you want, three continuum symmetries in the x, y, and z directions. And therefore there must exist three modes, or a threefold degenerate mode, or well, at least three low energy modes in this state. And these modes are exactly the phonons that we're going to find. Of course, in our solution, as we will see them automatically, and they're not going to be related to a spontaneous symmetry breaking itself, but it's very interesting. This connection is very interesting because you can sort of predict the existence of such low energy modes just by the fact that certain types of structures form out of symmetric systems. So in the rest of the lectures today, I'm not going to be alluding to this Goldstone theorem. So this was just a remark for those of you who are interested in advanced understanding or advanced subjects. But I just wanted to make this remark because I find it quite illuminating, because you can see the appearance of this very powerful, the application of this very powerful theorem in a very simple example.